Okay, this is the fourth of 4 lectures on rotational motion. And in this video, we're going to talk about rotational equilibrium. So we just learned about torque, and we know that if something is in static equilibrium, all of the forces in the x direction and all of the forces in the y direction add up to 0. And we've done lots of problems where we've, used that as a way to set up problems. Well, it's not so different when you think about something rotating. If something is torquing one side of the object, if you want to keep it from rotating, you need to torque it the other way. So the sum of all the torques has to add up to 0 for it to be in rotational or static equilibrium. So let's just take an example here of this little kid, okay? Let's say that this lady is holding this, and you've got a little kid that's pushing down on the board, and you've got a father who's pulling up on the board. So the radius of rotation is the distance between the axis and the person sitting or the person pulling. And remember that if something rotates around clockwise, like this little kid is going to tend to make the board rotate down, that has a negative torque. The torque would just be equal to his weight times the distance to him, and it would be a negative number. And in order for the father to counteract that, he's going to apply a torque upward. And his force that he's holding upward has to be such that when you multiply it by the length here, that it adds up, that the length, total length here, times the forces he's lifting with balances the little kid's torque. So the negative torque from the little kid has to be equal and opposite to the torque from the dad. Now, remember that if you want to have a large torque, you need a large radius, but that also means that you don't need to pull up with as much force. So notice that the weight vector here is bigger than the lifting vector, F2. Why? Because in order for there to be the same amount of torque between these two forces, this is a smaller force, so it has to be further away, versus this force, which has to be, which is closer. So if you have a small r, you're going to have a larger force needed to provide the same amount of torque as a small force with a larger r. So we have a 100-kilogram man sitting 1 meter from the fulcrum of a seesaw. Where does a 50-kilogram child have to sit on the other side to balance the torque? So remember that the absolute value of the torque of the man has to be equal to the absolute value of the torque of the child. And the torque is just going to be, they're both sitting on this. It's just two people playing seesaw. So both of their torques are down. The man is going to make it go one way, and the child is going to make it go the other way. But as long as the magnitudes are equal, they'll be in equilibrium. So the torque of the man would be his weight, 100 times 9.8 times r, 1 meter. And the torque of the child would be 50 times 9.8 times x. Notice that the child has half the weight as the man. So that means the force is in half. Therefore, he has to sit twice as far as the man does to exert the same amount of torque. Also, remember that when forces have both vertical and horizontal components, in order to be in equilibrium, an object must have no torque and no net force either in the x and y direction. So think about a lamp that's adhered to the wall. So this lamp, first of all, is pulling downward here, is pulling downward, producing a downward torque. And this force here, the wall has to, so you see we have a supporting rod right here. That supporting wall has to pull with enough torque to counteract the torque of the lamp's weight. So once again, if you have something that's pivoting right here, like say you have a meter stick hung by, a rope, it's got to be balanced at the point where the torque on one side equals the torque on the other, and that is called the center of mass. You can find the center of mass if you take an object and you hang a string from different points on it, and you draw that string, and you rotate it around and draw where they intersect is the center of mass. It's the center of equal mass distribution. It's not always in the center of something. If you had a donut, it would be in the very center of nothing, right in the middle. When we deal with systems that are rotating, and we start looking at rotation and forces, it gets to be a little more complicated because we have to look at the pulley and its rotational, the torque on it, and the mass. And all our problems so far, we haven't ever really dealt with the rotation of the pulley because it gets confusing, and it's really beyond the scope of this class.